Welcome to the Fractional Calculus Seminar Series. Today we have Professor John Gibbon, who joined the Mathematics Department at Imperial College London in 1980 as a 31-year-old lecturer. He has been an undergraduate in mathematics at the University of Birmingham from 1967 to 1970, and he studied for his PhD at the University of Manchester Science and Technology from 1970 to 73. For 5 years, he had been a postdoc positions, and then he held a lecturership position at the UC Dublin for 2 years. His early work had been on nonlinear waves and solitons before he moved on to the study of Navier-Stokes equation and Euler turbulence. We are very happy to host you here today. You may please begin your talk.
Well, thank you very much for this invitation to speak. I hope everybody can hear me, and I hope I've prepared properly. So I'm going to move into my first slide. You know, every talk needs some form of motivation. And the subject of turbulence is one of these great unsolved problems that's been around forever. Richard Feynman claimed that it was the last great unsolved problem of classical physics. I think that's probably true. And like almost all subjects that are quite old, they tend to split into tribes and clans of different groups get together and have their way of doing things. And then the different groups hardly talk to one another, and they become sort of sat in their concrete bunkers doing their own thing, and they hardly actually move outside. And one of these problems, you actually see this in turbulence theory, and I haven't stated all the tribes here. There's the classic Kolmogorov's statistical theory, which many physicists and engineers have worked on since 1941. And the great textbook in this area is Uriel Frisch's book, Turbulence, the Legacy of A.N. Kolmogorov, which is now 30 years old. And this is culminating in what's called the multifractal model, which we'll talk about later. That's one grouping. Another is the grouping of mainly analysts who talk about solutions of the incompressible Navier-Stokes equations in terms of regularity as a sort of PDE. And you would include in this fractional Navier-Stokes equations, where the Laplacian is replaced by minus Laplacian to the s. And I haven't included, now those are two of the big groups, and they really have different languages, different attitudes. They're trying to solve almost different problems. And I want to try and resolve this sort of issue and see if we can see if there's a bridge between the two. Now, of course, I haven't really included everybody. You have engineers who do turbulence modeling. You have engineers who do Reynolds averaging. There's all sorts of different groups doing these things. But then in recent years, you can add another tribe, and that's what's called active turbulence. And in these recent years, what's called flocking phenomena, where you have groups of birds or flocks of birds or shoals of fish or of bacteria that act collectively together. And they collective phenomena where they like swim in a fluid. And what the PDE main equation for this is called the incompressible Toner-2 equations that model flocking phenomenon. And you can see here, it's like Navier-Stokes on the left and Ginzburg-Landau on the right. And so there's a very much a relation here between this and the other two. And what I'm going to do in this talk is try and do 4 parts if I've got time. The first part, which is quite short, just 4 slides, trying to explain traditional Kolmogorov theory and the multifractal model. Most people know it, but there are some who don't. I'm going to go through it and summarize it. Then I'm going to do the same sort of summary, a little longer, on incompressible Navier-Stokes. What do we know? What would we like to know? Because there's many things we don't know. And this is where fractional Navier-Stokes would fit in. And then I want to try and show that there really is a correspondence between the two in part 3. And these ideas, I'm writing another paper on this much more simply, but these ideas can be found in this paper I wrote in 2023 in Physica D. And then, and only then if I've got time, I want to do part 4 on active turbulence. And that part, what's called the VTEC model and the incompressible Tony 2 equation, that part has been done in collaboration with Kiran Kolaru, Nadia Pavan and Rahul Pandit. Kiran's now in Nice, but was originally with Nadia as Rahul's students in the Indian Institute of Science. And I want to show you that many of the things that we can discover here actually are applicable here, if I can get to it. So let's begin. Part 1, multifractal model. Now, I've sort of stolen this picture from Uriel's book, and it's a sort of cascade picture where you start with big vortices, and the vortices split into 2, which split into daughter vortices and divide ever further. And it's like a pictorial model of an energy injection, a cascade. And then the question is, what happens when you sort of hit energy dissipation? Because numerical simulations show that ever finer vortical structures appear as our resolution increases. Scales much smaller than the Kolmogorov length. And Richardson, because it goes back to Richardson, this idea of a cascade, Richardson and Kolmogorov basically believe that viscosity ultimately halts this process, that once you sort of hit the sort of viscous scale, then sort of everything stops. And there was this little parody that Richardson wrote of Jonathan Swift's poem. You know, big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. The question is that really true? Because Mandelbrot, in his 1974 work, suggested that the cascade process is fractal and that these length scales get ever smaller and might actually, the inverse process might diverge to infinity, or the scales actually go to 0. The question is, who was right? So let's move on. So let's do a little bit of what's called K41. That's Kolmogorov's original theory. You take the Euler equations, incompressible, and if you just do a bit of trivial mathematics on the back of an envelope, you'll discover they're invariant under this scaling, that you take some lambda, and you say d by dx is d by dx prime times lambda to the -1. And then you'll find that with this particular scaling, with some scaling parameter h, which is arbitrary, and that's very important that h is arbitrary, the Euler equations really are scale invariant under this. So, if you're a probabilist mathematician, you'd want to define your U as some random field over some specified probability space. But you can be much simpler than that, because dimensional analysis says that. And I ought to stress that K41 is really applied to homogeneous isotropic flows. That's very important, homogeneous isotropic flows. But the standard tool is to take what's called a structure function, where you take the velocity field at some point x, vector x, then you draw a sphere around x of vectorial radius r. And then you take the difference between u at x plus r and u at x, raise it to the power p, and take some statistical average, doesn't really matter what. And according to this scaling here, the scale invariance, this structure function, the P structure function. And now this tilde means scales like. It scales like R to the HP. Okay. Now, here's the crux. That what Kolmogorov theory is an axiomatic theory. There's a set of one of its axioms is that the energy dissipation rate should in effect be independent of H. It says it's basically constant. If you're going to demand that, and you also use dimensional analysis, basically this says that H has to be a third. Okay. Moreover, so that fixes H as far as Kolmogorov can tell. It's free there, but it's basically fixed here. Moreover, you can do a calculation for Navier-Stokes and discover that there's an exact result for F3. And that's minus, called the 4/5 law. It's minus 4/5 epsilon R. Okay. Now, the point is it all looks very nice, but is it actually true in reality? If you actually do some experiments, if you do numerics, and one of the problems that was discovered in more recent years is that if you take your data and you plot, and again, this is from Uriel's book, zeta p, which is basically the exponent of R, against p, you can see here exactly that when you've got one going across and there's 3, where R is what 1, you see. And so here's the line P over 3. Actual data doesn't stay on that line. It doesn't go like P over 3, as this says it should. It actually goes a concave curve below it. So zeta P is not actually, in reality, P over 3. Now, there are many other things to Kolmogorov's theory, like, the minus 5/3 spectrum, etc., which we're not going to go, and what's called the Kolmogorov length, which is the specific inverse length scale, which is the cutoff. But in essence, the fact that it doesn't go according to these rules means that something else is going on. And what is interpreted is what is called in the business intermittency. That is, if you take your box of isotropic homogeneous turbulence, it isn't just a random field spread all over the box. And in fact, you've got a fractal clustering of wave numbers in frequencies. So if you look at a signal on a screen, instead of it just being sort of random signal, you'd find violent spikes. You'd find large periods in time of relatively flat output, and then you would find narrow violent spikes, departures from space-time averages, and that's what is actually called sort of intermittency. That is said to be the origin of this. Okay, and it was this here that I'm describing, which was the motive. Now I've got a picture here, and you've got a description, in effect, visually of intermittency. This is the Texas A&M database, a 4,096 cube database at Reynolds Lambda 1,000. It took 100,000 processors to do this. This was one state of the art, but now many of the calculations have gone up to, you're talking about now 18,000 cubes. Some of them are 20,000 cubes now. But they're not essentially seeing anything different. If you look inside your box, you see here, they've taken a little cube, they've sort of opened it out and expanded it. And what you're seeing are intense vortex cubes. This is a sort of snapshot. Intense vortex cubes where omega squared in red clusters, and where the what's called the dissipation, Sij is a half U I comma j plus j comma I around the outside of the tubes. And this is an example of intermittency where vorticity strain is not spread around randomly around the cube, but clusters into these sets. Now, the multifractal model of Parisi and Frisch, 1985, basically used a probabilistic argument. They said, well, sticking to the 8 to the third rule is too severe. And so they introduced a probabilistic argument that basically said, well, the energy dissipation rate need only remain constant on the average in some sort of probabilistic manner, which allows H to roam free. And you've got, therefore, departure from H is a third. And the way they did it is this. There's really an older and a more modern way. I would actually say that if you're interested in this, if you don't know much about it and you're interested, Uriel's book is quite good. But there are notes by Greg Ike on his website in Johns Hopkins, unpublished lecture notes, which are really very, very good. And I recommend them, chapters 3C and 3D. And essentially, the argument's like this, that you say that you take the PR of H, the probability of observing a given scaling exponent H at the scale R, and you're assuming that each value of H belongs to a fractal set of dimension D of H. So D of H is the fractal dimension. C of H would be the codimension. So you can either write it like this or like this. It makes no difference. And then when you work it through, and I'm not going to give the detail, when you work it through, and it's only a matter of a few lines, the structure functions, instead of taking the form HP with H is a third, they take the form what is called zeta P, and zeta P is now this object, the inf of HP plus C. Now you can see that if you were just assuming that you were in a 3D domain, so D was 3, no fractality, you're in a 3D domain, C is 0, D is 3, you're basically back to your HP again as on the other slide. But now you're in a fractal domain, and when you now what you have is, if you go back to my previous slide but one, you find that S3, the 4/5 law, goes like R to the 1. And so zeta 3 must be 1. And if zeta 3 is 1, that actually tells you, you work this through, you have to use what's called a Legendre transformation. When you work this through with zeta 3 is 1, it actually tells you that D of H is bounded by, the less than or equal to is because of this inf, 2 plus 3H, or C is greater than 1 minus 3H. Now you can see that if you go back and put H as a third, then of course the upper bound is 3, as it should be, and C will be 0, the lower bound. But you've now got this range of H, so you've got a range of fractal dimensions. This theory doesn't give you a lower bound on H. Basically, H is a third is really like your upper bound, but it doesn't give you a lower bound on H. And I'm going to come to that later on with Navier-Stokes. But in essence, this is a sort of like a quick 3-slide summary of the multifractal model applied to isotropic homogeneous turbulence. You see, there's nothing dynamic in it. There's no evolution in time. We're talking about a statistically steady problem. So now let's move on to part 2. Navier-Stokes, incompressible. Well, I think everybody's seen Navier-Stokes incompressible. We're going to take this simple domain, 0L cubed, an L2 bounded forcing, okay, So div represents incompressibility. And now there are certain points we need to, how do you numerically deal with the pressure? Well, you take div is naught, apply it across the equation, and that tells you that Laplacian P is minus ui comma j, uj comma I. And so you've got a Helmholtz equation to solve numerically. So at each time step, what you have to do is solve this equation, which is one of the reasons why it's so slow. You know, one of the reasons why in Navier-Stokes you're constricted by this, having to do this at every time step. Now the notation is that this bracket means time average, and this double here is basically the LP norm. Okay, basically that should have a 1 over P outside. Excuse me. So I'm going to use the designation that U naught is basically the L2 average of the velocity field, which is easily proved to be bounded. So that's a good object because it's a bounded velocity. You would define your Reynolds number this way and your Grashof number based on the forcing. The forcing is in the Grashof and the Reynolds is the system response. Okay, now the Clay Prize problem at D3 is, can one prove regularity of solutions, which is an open problem. Nobody has ever done it. And I'll come to that in a moment. And because this is a fractional seminar, it actually has a long history. Jacques-Louis Lyons, as far back as 1959, he basically proved Navier-Stokes are regular in the sense proved existence of uniqueness of solutions for basically minus Laplacian to the S, but S has to be greater than or equal to 5/4. S is 1 is not enough. So let's move on. So what do we know? What we know and what we would like to know, and then Navier-Stokes said two very different things. Okay, so let's take the definition of these semi-norms here, gradient to the NU. We have Leray's energy inequality here, which is just simply, in effect, there's a process you have to go through, but in effect, hitting the equation of U with U and integrating. And if you want a textbook, a good textbook, modern textbook, Robinson, Rodrigo, Sadowski, 3D Navier-Stokes Classical Theory is a good book. So, but you go back to Leray, 1934, the existence of a weak solution is this, that for all initial data, there exists a global inclined weak solution such that, in effect, is this equation here. H naught of t, integral of h1 is bounded by this. Now, note that we have boundedness of h1, not boundedness of h1 pointwise in time, and this is the difference. This is the big critical thing, that having the time average h1 bounded is good, and that's excellent, but we would like to prove that h1 is bounded pointwise in time because that would give us existence. And that's what we don't have. I would point out that when n is 1, the integral of grad u squared is exactly the same as the integral of omega squared. In higher LP norms, it's not true that grad u in higher LP is the same as omega in a higher LP, but it is true and P is 1. Okay, so what has been proved? Well, Ladyshinskaya in 64 proved regularity for short times and small initial data separately. Luke Tatar in 78 proved that the time average of U infinity was bounded, a result that was often buried and forgotten. And even more buried and forgotten was a result by Foyas, Giope, and Tamam in 81, that if you take these HNs, defined up here, to the power 1 over 2n minus 1, their time averages are bounded for all n greater than or equal to 1. what I call FTT81. Now, for some reason, excuse me, I'm going to have a mouthful of water. This result was published in Communications in PDEs in its first volume. And it was a good journal, but it wasn't a well-known journal at the time, and it got buried. And an awful lot of good people in the field didn't know about this result. 10 years ago, I started banging around telling people about it, saying, you really need to know this. It's very important. It's the best result since Leray. Okay, so we keep this in mind. And then in 82, Caffarelli-Cohn and Nirenberg proved the singular set has zero one-dimensional, Navier-Stokes singular set has zero one-dimensional space-time Hausdorff measure, which basically means if you're like in 4 space, 3 space, 1 time, singularities, if they have zero one-dimensional space-time measure, then basically saying singularities are extremely rare events. And if you want a much more up-to-date on the very latest, then Bedrosian and Vikol latest book, AMF 2022, is recommended. Okay. Now, we would like to prove that H1 is bounded for arbitrarily long times, but nobody has been able to prove that. In 2D, you're okay. Now, if we curl the Navier-Stokes through and take the vorticity equation, what you find is, of course, you've got this extra term on the right-hand side, what's called omega dot grad U, what the engineers call a vortex stretching term. Now, in 2D, of course, this is 0. Omega, grad lies in the plane, omega comes out of the plane, perpendicular, so this is 0. And that's the bad guy. That's the guy that causes you all your intermittency, all your difficulties. And it's not there in 2D. And so you can see if that's not there, then it's trivial to prove that omega is bounded in every LP. And that's enough for regularity. So fundamentally, 2D Navier-Stokes is a different animal. You find a lot of people saying, oh, well, 2D, 3D, as if they're the same thing. They aren't. They're a fundamentally different animal because this is not there in 2D. But in 3D, this term causes you all the trouble. And this is the origin of the intermittency that we were discussing earlier. Now, are there regularity criteria? In other words, if something were true, then it would be regular, even though you haven't actually proved it's true. And it actually the best one goes back, it's often attributed to Serin in 63 and then Ladishinskaya in 64, but actually was written down by Prodi in 59. And that says that if U is a Leray-Hopf weak solution, of this type, L to the P in time and LQ in space, then there exists a unique smooth solution if P and Q obey this relation. Okay, now that's not true when this is Q strictly greater than 3. The case Q equals 3 was Escorio's Sereg and Ferak in 2003, which in effect says that if U in L3, you see, U in L3 for all time, P is infinity, and U in L3, if U in L3, it could be proved to be bounded, then you have full regularity. Of course, nobody has actually proved that. Another way of expressing it is there exists a unique smooth solution if the time average of U infinity squared is bounded. Well, we know the time average of U infinity is bounded. That goes back to Tatar, but nobody has proved this with the 2 in it. Likewise, if that were bounded, Navier-Stokes would be regular, but the only result we have is with a power of a half in there. Okay. Now, can we just a moment. I'm losing the top half of my screen with all the various things, but never mind. Can we summarize all this together? Because, you know, you've got all these different regularity criteria expressed in different ways. They must all be equivalent in some way. And this equivalence is important, as I hope I will prove to you. And what I'm going to do is this, is sort of set up what it is that we need. And I'm going to take these, in effect, not norms, m gradients to 2m. Navier-Stokes, now you see Euler has this invariance property where you've got h minus 1 and you've got h here. But that Navier-Stokes doesn't have that property. It's only invariant when h is minus 1. Okay, so your h minus 1 would become minus 2 and your h would be minus 1 here. And these Sobolev norms have this invariance property, okay, according to this. And what that's really telling you is that if I form this object with an L to the 1 over alpha, nu to the minus 1, that is a dimensionless object, has no dimensions, and this alpha is actually a property, really, of this invariance. It's 2m over 2m into n plus 1 minus d, and d is the dimension, either 1, 2, or 3. Okay, now note that when m is 1 and n is 1, this object is 2 over 4 minus d. Now, I've expressed where I've written this down in this particular paper, but it's also, now keep this in mind, this f. And basically, we have the theorem that says that if you take this f to the 4 minus d times the alpha, which I've written down, take its time average, then that is bounded by set of constants, Reynolds cubed. That's true for n greater than 1, and it's true for n is 0, but m has to be greater than 3. Now, just let me give you some cases, and I will show you that all those previous separate criteria are all built into this one line. So we're going to do d is 3. When n is 1 and m is 1, essentially that gives you exactly the standard Leray energy estimate. That's exactly that. Now the time average of h1 is bounded. Okay, so I'm now going to take m is 1, but take n greater than or equal to 1. And there, basically, you've got the FGT result, the one that was lost, but which is the great result that was found in 81. If we take n is 0, but m is infinity, then time average of u infinity is bounded, and that's Tartar's result from 1978. Okay, and if I take m is infinity and now n is 1, then I get this power of a half. Okay, so all these are known regularity criteria. They're all basically come out as special cases out of this. This is really what you have for, this is an expression of all the Leray weak solution results all roll together basically in one line. And it's really to do with the symmetry, the fact that Navier-Stokes has this invariant symmetry, which gives rise to this object alpha, 2m over 2m into n plus 1 minus d. And so now, if you said, well, okay, this theorem here is what you've got. That's what we know. What would we like to know? Because what we would like to know is is when would Navier-Stokes actually be? What's the criteria for Navier-Stokes actually being regular? And the answer is, if you work it through, that you need a power of 2. Of course, nobody has proved this, but that's what you need. You need a power of 2 there. If this was bounded, then you've got enough for existence of Navier-Stokes strong solutions. Now, given that this is so, where is the Prodi-Serin-Leditsky condition for regularity, the one that goes back to 1959? Well, their criterion was that if U is in LP in time, LQ in space, then there exists a unique smooth solution if this is true. Well, simply take N is 0, P is 2 alpha, now N is 0, so you've got alpha 0 M, and take Q to be 2M, because Q is something in 2M, and that's what your norms are, you're in 2M. Okay, and so that will be 2 over alpha 0 M, 3 over 2M plus 1. And given what we know that alpha is, that's exactly 1. So the Prodi-Serin condition is built into this theorem here with N is 0 and P is this, and Q is 2M. And the Ascurios-Serrier-Ferrat result that U3 controls regularity, you can actually do by integrating the pressure and working this through. And so that's also there. But this is a theorem that you would like to prove, but we don't know is true. And maybe isn't true. You know, these great challenges, and everybody tries to prove them, but it may not actually be true. It could be, it's a heretical thing to say, but it could be that basically Leray's weak solutions is all we've got. Maybe Navier-Stokes isn't regular in the conventional sense we understand. Excuse me. Now, what has this got to do? Oh, well, just let me do one digression. Last year in this seminar series, my good friend and collaborator, Daniel Boutros in Cambridge, who's a student of Idris Titi, we wrote a paper in nonlinearity on fractional Navier-Stokes, and Daniel actually gave a talk in this seminar series. So you're taking A, the negative Laplacian to the power S. And just to give a summary, in terms of what we've been talking about, that for fractional Navier-Stokes, if S lies in the range 0 to a third, then it really behaves like Euler. Non-uniqueness of Leray-Hopf solutions. Maria Colombo, Rosa, Bedrosian, and Vicol. And when S is between a third and 1, there's a Prodi-Serin criterion involving, basically, it's like add to the S, in L infinity to the 2S over 3S minus 1. And you can see it basically fails at S is a third. And when S is 1, it just becomes basically grad U in L infinity, which is the standard Cato-Maida result. Then there were 2 results for S is greater than 3/4. The generalized Caffarelli-Cohn Nirenberg result and local energy balance. And now, where does Leray-Hopf kick in? Well, the answer is when S is greater than 5/6. Okay, so essentially, the famous Navier-Stokes at S is 1, S is 1 is nothing special. The properties of Navier-Stokes that we know in terms of Leray come down toward 5/6 and exist all the way up to 5/4. And then they change again because of Jacques-Louis Lyon's result that once you go through 5/4, you do have your existence and uniqueness. Okay. But essentially, as I say, 5/6 to 5/4 is really where standard Leray-Weak solutions lie. Excuse me. Okay, so part 3. So that's Navier-Stokes summary. So part 3. Is there a correspondence between Navier-Stokes and the multifractal model? Well, I'm going to try and suggest that there is. So let's consider this Sobolev norm. Now, what does M is 1 mean? Well, you think of this physically. You're sitting in a box and you're sort of watching if you've got some special glasses on, and you can actually see the vortices washing around. But basically, L2 is an average wash over the box. But as you increase M, okay, if you increase M, basically you're seeing more and more intense features. They stand out more against the background, until finally you reach the maximum, the most intense point where M is infinity, and then that's the L infinity or the soup norm. And so M acts as like a focus control on a telescope. It's like taking a telescope and looking at features in the sky. And if you just have M is 1, then you're really just fuzzy. You're not really doing anything. You're just sort of focusing on the whole sky. Okay, but as you zoom in onto the brightest or the brightest clouds, you're raising M, so it's like a focus until you reach M is infinity and you've hit the most brightest cloud. So it's like a focus control on a telescope. So let's think of M in that way. Now, this labeling, subscript labeling, the subscript labeling basically means that L2 in a volume of d dimensions basically means that you're doing, as I say, n derivatives in L2m in d dimensions. And now I'm going to have this alpha n md, which is this thing here. You're in L2m here, d is a dimension, and n is a number of derivatives. So divide through by m. And now it's 2 over 2 into n plus 1 minus curly dm. And that's curly dm is a dimension d over m. And that's exactly the same alpha that you would have, where you've got, it's recast as n derivatives in L2, okay, on a set which will designate as Fm, but this now has a range of dimensions curly dm, because this place is the part where the dimension goes. This part is the order of the LP norm. So you're now just in L2 on a set which we'll call FM. Now, we don't know any more about FM other than this, but it does have this range of dimensions, so it's mimicking. Okay, so we're suggesting that FM is multifractal in character, and it's got this range of dimensions, curly dm, which is main dimension d over m, where m is from 1 to infinity. And this is what I was trying to explain in my Physica D paper in 2023. Now let's use this. Okay. Now, here we come to the critical point of comparison. How are we going to make a correspondence between the multifractal model, which is for homogeneous isotropic turbulence, steady, and Navier-Stokes, which is a PDE, which is evolving from initial data. And I would suggest that you can really only make a correspondence. You see, turbulent flows become mature. There are numerical, Orsag and Patterson in 1971 actually have a criterion based on the third velocity derivative, which basically shows you whether your turbulent flow has actually become mature. And once you've become mature, then at that stage, I think it's reasonable to make a correspondence. To say, okay, let's make this correspondence that the DH, the set of fractal dimensions for the multifractal model, and the curly DM from Navier-Stokes, I'm going to equate the two. Now, remember, DH was really, most physicists put equals here, but it's really less than or equals. So I'm going to put the 3 over m for dm equal to dh, which is less than 2 plus 3h. Now, what do you get? Well, it's very simple. Essentially, h min is m minus 1 minus 2/3. So when m goes to 1, you're essentially picking up 1/3. When m goes through all its, like the telescope, all the way from 1 to infinity, you come down to minus 2/3. Now, Kolmogorov's theory gives you the third. It doesn't give you minus 2/3, but this is telling you, in effect, that if you're going to have a correspondence, really your h is bounded within this minus 2/3, 1/3 range, which actually, as we'll see, turns out to be reasonable. And now, let's see what the consequences are. Let's now look at our theorem. Now, I haven't proved that this object is bounded, but I'm just going to say consider it, where we're taking 4 minus the dimension times alpha, which I had proved in my earlier theorem for Navier-Stokes when I just had little d, the domain dimension there. But I'm going to say consider that with little d replaced by curly d. Think of it when n is 1. And when you actually do that, the 4 minus dm cancels with, you get a form, you've got 2 into n plus 1 minus d on the bottom line. So when n is 1, you've got a 4 minus d. So this factor of 4 minus d cancels, and it simply leaves you with grad u in L2. Okay. But now you're integrating over this fractal domain Fm, not over the full volume. Now, I don't really know what that integral means, because we don't know any more about Fm other than the fact that we're designating it as a multifractal set with this range of dimensions. But I'm basically defining this as my mth energy dissipation rate, and that has all the dimensions of an energy dissipation. Now, we know, luckily, that Fm is buried. It's in the full domain. This is positive. So we actually have an estimate for this in the full domain, and when you write that in, you get the following. And now it's trivial, because these objects epsilon to the m nu to the minus 3, that defines a set of inverse lengths. And when you work out what they are, you get Reynolds to the 3 over 1 plus dm. Okay, well, dm now ranges, remember, from is 3 over m. When m is 1, d is 3, and so you've got Reynolds to the 3/4. Well, that's the Kolmogorov length. Reynolds to the 3/4, only when m is 1. But now you've got the full range of 3 over m here. And when you actually look at this 3 over 1 plus dm, what is its lower bound? In other words, if you minimize this thing, if I minimized it, what would I get? Well, if I minimized it, what I get on the right-hand side is Reynolds to the 1 over 1 plus h. And that's exactly the scale that Paladin and Vulpiani in 1987 said was the range of scales for Navier-Stokes from the multifractal model. Exactly that. So this correspondence is giving all the right answers with the right in inverted commas. Okay, so how are we doing? 16. So I would argue that what we're seeing what we're seeing is a sensible set of results coming out from this correspondence here. Okay, now what is this? What is this PV scale? And I've got a slide, which is a relatively new one here, because Paladin and Vulpiani, how can you pull out a length scale with H out of Navier-Stokes when Navier-Stokes doesn't have H in it? It's only Euler. Well, here's the way I think to look at it. You want to have a length scale, small length scale, between 0 and L. For some typical velocity u, you can work out an invariant scaling for Euler, and it looks complicated, but it's really like the previous one. But the one I wrote down on the first slide didn't take any account of dimensions. It was invariant, it was dimensionless Euler to dimensionless Euler. And when you're doing proper physics, you've got dimensions to take into account. So if we take dimensions into account, this is the way you do it. You have to have an inverse time here to cancel the dimensionality of t. You have to have a u to take account of the dimensionality of u here. But that's all that is. Now, what is the Reynolds number? Well, the proper definition of a Reynolds number is this. Now, the reason I'm doing this, just let me take another drink. Is that Paladin and Vulpiani had a Reynolds number in their paper that was not a Navier-Stokes object at all. It was actually a sort of physicist, fractal physicist Reynolds number that was based on the integral of omega squared. Well, that's fine. In isotropic turbulence, that's a constant, but it isn't for Navier-Stokes. It's one of these things that we would like to prove is bounded and isn't. So it isn't a proper Reynolds number. So let's do this properly. Let's write down a proper Reynolds number and then say two assumptions that this proper Reynolds number is equal to its standard descriptive definition. And if you look in fluid, now, if you've ever done a first fluids course, you know, given by applied mathematicians or engineers, the descriptive definition of Reynolds number, that it's the inertial term over the dissipative term, okay, which is u dot grad u over nu Laplacian u. And moreover, Reynolds should be greater than 1, which again is the classic definition that if you're going to not have laminar flow and you want turbulent flow, then Reynolds has to be greater than 1. Okay, well, let's just do that. Let's put this Reynolds equal to this and do two things. First of all, you can cancel Reynolds and you simply get this result here. And since eta is less than L, it has a lower bound of greater than 1. And secondly, now we can simply put here that leave the Reynolds here and put Reynolds greater than 1, greater than or equal to 1. And so that gives you this second result, that this is less than that. Now, we want this to be true for every solution u primed. And so we want to minimize our upper bound, and we have a minimum of this upper bound, it's 1. And so this therefore tells me that L eta to the minus 1 is greater than 1 and less than Reynolds to the 1 over 1 plus h, which is exactly the Paladin-Vulpiani scale. Except it's not equal to, it's a bound. So it's in effect like a little theorem. It's saying that if this is your invariant scaling for Euler with eta, which is free to take any value between 0 and L, then applied to the Navier-Stokes equations, eta is restricted by this result here. And I think that personally makes much more sense. And you can see now that that's where this Paladin-Vulpiani scale is here. Now, I think I've had 55 minutes. What I'm going to do is just do some very brief, just in 3 or 4 minutes, on flocking, because, you know, I talked about it earlier. So, I've only missed out one slide. Okay, so let's go over to flocking, and you'll see the reason why I wanted to at least mention it. This idea of flocking, where you've got what these are called murmurations of starlings. And it was Vicek and these other guys in PRL in 1994 said that this like corresponds to Heisenberg-ferromatic interaction, where you've got essentially, you've got a bird, and the bird basically, how it moves essentially is just, it takes account of its nearest neighbors, and then there's a little bit of random noise added on to make an analogy with temperature. Okay, now the Vicek model is real statistical physics, and you can talk about birds, fish, bacteria. The PDE equivalent of the Vicek model is the Toner 2 model 95 from these two papers, and it's essentially Navier-Stokes on the left and what is like Ginsburg-Landau on the right. And you've got these fixed parameters, lambda, nu, alpha, beta, which basically are like this. And then there is another equation called the Toner 2 Swift-Hohenberg, where you've got essentially the same left-hand side, the same right-hand side, but then you have negative viscosity and then a bi-Laplacian. So negative diffusion together with a bi-Laplacian. And that's like this part is like the Swift-Hohenberg equation. So it's TTSH. Now, this is work very quickly I did with Kiran, Pavan, and Rahul. Okay, if you take dimensionless ITT equations defined in this manner, then essentially you end up with two Reynolds numbers. Okay, Reynolds nu, which is your standard one, U naught L over nu here. This is exactly like Navier-Stokes here. Okay, you've got linear forcing, and then you've got another Reynolds number, which is based on this beta. Okay, so it's a richer problem because you've got two Reynolds numbers and not one. Now, the point about this, and after this briefly I'll stop, is that other than the linear forcing, and you can just treat that as a forcing term, the Toner 2 equations, they have the identical scaling properties to Navier-Stokes, exactly like that. And therefore, it's got all the, it's got all the same properties that Navier-Stokes has got. So you've got an alpha, 2m over 2m into m plus 1 minus d. You have a theorem Fn md, 4 minus d. You have exactly a theorem, but now for dimensions 2 and 3. Okay, and you can do exactly the same thing as we did. And you could also lift over the same multifractal properties that we did in previous slides. And you can find energy estimates. Now, the one extra thing that you have, you know, you've got bounded energy, you've got bounded H1, but you've also got bounded L4 because of this minus U mod U squared term. And that gives you sort of extra information. And I'm not going to show you any because this is a lot of, but Kiran did a whole lot, Kiran and Rahul did a whole lot of plots of the P's and Q's and all the different N's and M's. And it's really a very considerable amount of work that you can do. But the point is that it's very similar to Navier-Stokes because it's got a much richer structure, precisely because you've got two Reynolds numbers. So it's a very nice model. Very nice indeed. And I think what I will do, having done that very briefly, I will stop there and pass it back to you. So thank you.
Thank you very much. That was actually very exhaustive talk. Are there any questions? You may please unmute. You may please raise your hand, and I'll uh, I'll call out your name as they appear on my screen.
I've got just two screens worth of references if people want to see these.
Yeah, sure. I don't see any raised hands, so if somebody still has a question, you can unmute your mic and go ahead. Yeah, okay. Okay, so I have like one or two very trivial questions. So I quite enjoyed that you plugged in DM as DH as a multifractal model, and that seemed to give the right scaling results
Yes.
on slide 16.
Yes.
So, but those were done for the case of Navier-Stokes equation.
Yeah.
Do you have something similar for the fractional Navier-Stokes of Lyon's?
Well, that's a very good question. I've been thinking about that. I don't fundamentally see any you could only do this process of comparison when S is between 5/6 and 5/4, because that's where you've got Leray-'s weak solutions, and therefore you would have all that class of time averages in the way that we have for standard Navier-Stokes. You've got all that, but it wouldn't work. It wouldn't be any comparison when S is less than 5/6 and greater than 5/4. Well, it's a different animal because, of course, it's fully regular.
Okay.
But in principle, I think you can do this in that region.
I see. I see. I see. So one of the reasons I was asking this question, because I have a previous work which I called it fractional Reynolds average Navier-Stokes equation. So basically, what happens is that you take the Navier-Stokes equation and then you time average it, and then in the diffusion term you fractionalize it, which I do it in a different way. The definition is a bit different. But in those equation, U is a deterministic field.
Yes.
But nonetheless, because of this time averaging process, I think there must be I must have some clue on what will be the fractal set for such a case.
Yes.
This fractal set could be could be like time averages of a certain window of a certain window in time.
Okay.
So that's the line. Those are the lines I'm thinking, like, what exactly the fractal set would be.
Yes.
Because
Yes.
ultimately we are looking at the same field, just in with different lenses. So those were the lines I was thinking about,
Okay.
but I don't. But this is something, an object that I just came across, so I don't really
Yes.
have
Yes.
proper answer to this question. But yeah, but that's actually a nicely put question. What is the fractal set over there?
Yeah. Well, let me just go back to, what is it, 16. Yeah, you see, the thing is that we don't know what the fractal set FM is. And if you want the full energy dissipation rate, you would have to sum over some measure of this thing, because you've got an infinite number from 1 to infinity here. And since you don't know what FM is, so you don't know what measure to sum over. That's what's missing in the problem. I'm sort of giving the answers here as to what the answer should be, without being able to look inside the crystal ball to see what the what the inside looks like.
Yeah, yeah. So if you mention sums, then maybe integrals over some periods of time, such that something holds, probably could be some clue towards it. So because Lyon's work on fractional Navier, which calls it the fractional Navier-Stokes. I did not know about Lyon's work during that time, but I also have a very similar equation, and that seemed to work, but for time average velocities and pressure and pressure, but at the same point, but these are two different lenses of looking at the same field. So
Yeah. Okay.
yeah.
Yeah, it's sort of interesting. Yeah. In a way, it's a little bit frustrating that you can get so close, but you can't. It says you can get so close, but no further.
No further. Yeah, I feel you. Yeah. But on a further note on it, I mean, but that was still a model because fractionalizing the Laplacian is still a model, and it's not something coming out of first principles of physics.
No.
So from the last 3-4 years, I've been thinking about it, and apparently I have a set of equations which I'm still calling it as fractional Navier-Stokes, but they come out of first principles. I gave a talk last year within the same seminar series, but those are far more complicated. But the nice thing about is that non-locality in the x direction can be different from the non-locality from the y and the z direction. So there is no reason that non-locality in any dimension should be same, because we also have a field that is homogeneous in one direction. So anisotropy was taken in consideration. But that was just a side remark anyway.
Okay. Thank you.
Do we have more questions or comments? I guess probably no. So this is a good point to stop here and thank Professor Gibbon for the nice lecture. It was very nice having you here, Professor.
Yeah. Thank you. It was a pleasure.
Yeah.